we can do double modular arithmetic. We take the usual A is congruent to B mod C, and then also apply mod D. For example, 1 is 7 mod 15 mod 24, because 1 and 7 differ by multiples of 15 and 24. And of course, this idea can extend. We can do triple modular arithmetic, or quadruple modular arithmetic, or quintuple modular arithmetic. But it turns out this is boring with the integers. Any double mod can combine into just one. However, this is not boring with polynomials. Sometimes they don't combine. So we'll mainly focus on them and see what kind of systems these double mods create. But before we do that, why are the integers boring? 3 is 53 mod 10. Mod 10 essentially means that 10 equals 0. So 53 is 5 times 10 plus 3, and 10 is 0, so the 5 disappears, and we're left with just 3. We can make this double modular arithmetic by applying mod 20. So then 20 is also equal to 0. But hello, that was already true. If 10 is 0, then any multiple of 10 is 0. This mod 20 is redundant, just like my next sentence. We can remove the mod 20 and nothing changes. What about this earlier example? 15 and 24 are not multiples of each other, but they can combine to make 3. So by setting them both to 0, we get that 3 is also 0. Mod 15 mod 24 simps to just mod 3. The reason is that 3 is these numbers GCD. And this GCD decree goes for any n and t. Their greatest common divisor is some linear combination. And we could find the x and y, sir, but that's a busier conversation. The point is, they exist. It's Bezout's identity. The GCD consists of some fuse of n and t. But I think that it would be good timing for me to quit with all this wordplay. Bezout's identity means that if we have a double mod, then both get set to 0, so the GCD is also 0, and we can just simp to a single mod. It's pointless to do double modular arithmetic. Well, it's pointless in the integers, but Bezout's identity doesn't work with integer polynomials. For example, with 2 and x2. Their GCD is 1, but they can't combine to make 1, since they both have an even constant term. So if we do a double mod, then both are set to 0, but 1 is still non-zero. Mod 2 mod x2 is not the same as just mod 1, even though 1 is their GCD. So what is the behavior of this double mod system? First, let's apply mod 2. This means that 2 equals 0, and therefore any even number is 0. So given a polynomial, the even coefficients are 0, and then the odd coefficients are even plus 1, so they equal 1. Every polynomial can simp into just 1s and 0s. It's kind of like binary.
Actually, it's not like binary. Binary is just notation. It doesn't affect...
It's kind of like binary, because we just have 1s and 0s. Okay?
No,
And we can further simp by removing the 0 terms and hiding the 1s. We end up with just powers of x. So that's mod 2. Now let's apply mod x2. This means that x2 equals 0, which also means that x3 equals 0, and x4 equals 0, and any higher power. So in some polynomial, all of the higher powers disappear, and we're left with just x and 1. This system only has 4 distinct elements: 0, 1, x, and x plus 1. Any other integer polynomial will be congruent to one of these. So now that we know the elements, let's make a table. Ow! Ow! Oh, my thumb! Okay, let's make a diagram. For this double mod system, we'll show how addition works for all pairs of elements. 0 plus 0 is 0, then 0 plus 1 is 1, 0 plus x is x, and 0 plus x plus 1 is x plus 1. We can similarly fill out the first column. Now, 1 plus 1 is 2, but since we're in mod 2, 2 equals 0, so we put a 0 here. Then x plus x is 2x, and therefore also 0. And the same thing for x plus 1 plus x plus 1. Here is the rest of the table. It has quite a nice pattern. But what about multiplication? That also needs a table. 0 times any a is 0, so we can fill all of these in. And then 1 times any a is a, so we can also fill in these. There's only 4 untrivial cells. X times x is x2, so because we're using mod x2, that equals 0. Then x times x plus 1 is x2 plus x, which simps to just x. And we get the same result here, since the inputs are just flipped. Finally, x plus 1 times x plus 1, which simps to just 1. We now have the full multiplication table. Together, these tables describe the double mod system. We only need to study addition and multiplication if we view this as a ring, a system that has well-behaved addition and multiplication. Of course, there is a more technical definition for a ring. Let's look at another ring. This time we'll use mod 2, mod x2 plus x. We end up with the same 4 elements, 0, 1, x, and x plus 1. This is because mod 2 works the same. Any polynomial simps to just powers of x. And then with mod x2 plus x, we can reduce any high powers. We can subtract a multiple of the modulus, since it equals 0, leaving us with a smaller polynomial. We then just rinse and repeat until all high powers are gone. So we have the same 4 elements, but do they act the same as the previous ring? No. Yes! Addition is the same. This was determined by mod 2, and that didn't change. But multiplication is different. The 0 and 1 cases are trivial, but what about x times x? That's x2. We can add the modulus, then zero out this 2, and we end up with x. X squares to itself. And the same with x plus 1. It also squares to itself. Finally, x times x plus 1 is x2 plus x, the modulus. So that is 0. And then this must also be 0, and we now have the full table. Along with addition, we have a full description of the ring. Compared with the last ring, only these 4 cells are different. And now we should try the other quadratics. Mod 2 mod x2 plus 1, and mod 2 mod x2 plus x plus 1. We see they all differ in this section. These are 4 different rings.
Actually, there are 3 different rings.
But actually, there's only 3 different rings. Here, if we swap the colors, columns, and rows, this ring is now identical to the one with mod x2. They're the same because they're both using the square of a linear polynomial. That's why we get a 0 here on the diag. Then this modulus is the product of 2 different linear polynomials, so we get 2 zeros off of the diag. And then this one is a prime polynomial, so we get 0 zeros, at least in this section. The behavior depends on how the modulus factors. So let's merge the 2 that factor the same. There's really just 3 rings here. However, there is a 4th ring that has 4 elements. In these cases, we took mod 2 mod a quadratic, giving us 2 elements. But we could instead use mod 4 mod a linear to get 4 elements. Here are the tables for this ring. Addition is different from the other rings, which we can see by focusing on purple inverse. This is because the integer modulus is different, 4 versus 2. But then the multiplication table is the same as the first ring. In both cases, we have a square as a modulus, so we get that 0 on the diag. Let's organize the rings into a table, addition in the rows and multiplication in the columns. But wait, there are 2 empty spots. What rings go there? Well, this addition table is mod 4. 1 plus 1 is 2, and 2 plus 2 is 0. This means that 2 times 2 is 2 times 1 plus 1, which distributes to 2 plus 2, which is 0. So 2 times 2 must be 0. Looking at the multiplication tables, this equation is true in the first one, but not in the others. They are not compatible with this addition table, so the spots will stay empty. Those rings are impossible. And it turns out, these are all of the rings with 4 elements. There are only 4 of them.
Actually,
For some extra fun, find the tables for mod 2 mod x3 and mod 3 mod x2. It's a nice exercise. Thank you for watching, and thank you to my recent coffee supporters. Ko-fi is kind of like Patreon, but I use them because they give viewers more options. You can support monthly, or just a single time if you're afraid of commitment. Plus, they're a smaller company. I like helping out the little guys. So consider supporting, and I'll see you in the next video.